So in this video, we're going to examine valence bond theory and the concept of hybrid orbitals to be able to try and have a framework to explain why certain atoms, like phosphorus in this case, have expanded octets. So, for example, if I had a molecule like this, which I've got the Lewis dot structure of PF5, according to Phosphorus'S atomic orbitals, its electron configuration, we have 3s2, 3p3. How can we explain that there are 5 bonds to phosphorus? Well, if we were to hybridize these orbitals and specifically promote one of the 3s electrons to a d orbital, and then hybridize those orbitals in the 3 subshell, in the 3 shell that have 1 electron, we would get 5 orbitals that have varying s, p, and d character. Those orbitals, those 5 orbitals would be called Sp3 D. And that would help to explain why phosphorus forms 5 bonds. So for elements in and beyond period 3, there is the opportunity to have expanded octets because of the possibility of forming these Sp3 D hybrid orbitals. Again, they're Sp3 D because I have 1 s, 3 p's, and 1 d orbital that hybridize and mix to give you that structure. And in those hybrid orbitals on phosphorus, that single electron in the Sp3 D hybrid orbital can overlap with an atomic p orbital from fluorine to give you that structure. So that's how Sp3 D hybrid orbitals theoretically are formed by central atoms. We can also think about the possibility of an Sp3 D2 hybrid orbitals. So for molecules that have a Lewis dot structure with a central atom that has 12 electrons, outer shell of 12, those 12 electrons can be accommodated by hybridizing 1s, 3p, and 2 d orbitals to give you 6 Sp3 D2 orbitals, each of which have a single electron in it, which are then available to overlap with the atomic orbital from fluorine to give you the following structure. So Sp3D and Sp3D2 hybrid orbitals help to try to explain why certain elements, specifically those beyond period 3, in period 3 and below, why those elements sometimes have expanded octets. One other point to make before we end this little vignette. So all of the orbitals and interactions we've talked about so far with regards to the central atom have been with regards to covalent bonds, or sharing electrons with those outer atoms. We know from previous chapters and in this chapter that many times central atoms will have lone pairs of electrons on them. What kind of orbitals do those lone pairs of electrons occupy? Depends on the central atom, but the take-home message is that lone pairs are always in hybrid orbitals. And hybrid orbitals either always hold lone pairs or form sigma bonds, single bonds. Hybrid orbitals are never vacant. They're never empty. You only mix the orbitals. You only provide the hybrid orbitals that are needed for a molecule. So they're never vacant and they never form double bonds. We'll talk about double bonds in a subsequent video. But take-home point is that lone pairs of electrons can be in hybrid orbitals. Hybrid orbitals are never vacant and they never form double bonds.